Hey guys, in this video we're going to finish off the semester talking about chapter 6, sections 1, 2, and 3. So in particular we're going to talk about transformations of parent graphs. In the last video we looked at vertical shifts and horizontal shifts a little bit. I want to go a little more into depth with those, and then we're going to talk about some other types of transformations, in particular vertical stretches, horizontal stretches and compressions, and then reflections across the x-axis and the y-axis. So let's get started. So last time we talked a little bit about parent functions, and really the only ones that you're going to need to know is everything except for the last row. So these last three, sine, cosine, and tangent, we're going to talk about in trig when you guys take trig. But these are the basic parent functions that we care about. So as I mentioned last video, these parent functions, they're just pretty boring, right? They're just, we have a line, we have a quadratic, a cubic, absolute value. You've seen all these functions before. And the idea is that they're not shifted vertically or horizontally, and they're not stretched or compressed. They're not reflected. They're just a basic graph. Okay, so what we're going to look at today is not only shifting these parent functions, but also stretching, compressing, and reflecting them. So let's go back over what a vertical shift is. So a vertical shift literally picks up a graph and moves it up or down. And the reason is because this guy right here, this f of x, is our output, or the height, right? And we're simply, when we apply a vertical shift, we're simply adding or subtracting a number to the output. So we're not doing anything to the input, we're just shifting the height. So if we have our function and then we have a plus 3 after the function, this means that we're picking up the function and we're moving it up 3 units. On the other hand, if we take 2 away from our output, then we're keeping all the x values the same, so all the inputs stay where they are, but we're shifting the output values by 2 units. We're moving the graph down 2 units. So let's take a look at an example. So the parent function that I'm interested in this example is f of x equals x squared. So that's going to be this guy right here, this quadratic function, parabola. And what I want to do first is I want to just get some key points here so that I can transform the function. So to get the key points, you just pick some numbers on the left and the right side of the vertex, and then you put them in the function and get outputs. So if we put in -1 into x squared, -1 squared is 1, so that's our output. 0 squared is 0, 1 squared is 1, and 2 squared is 4. Okay, so those are our outputs. And what the vertical shift tells us is, hey, all of the inputs are going to stay the same. I'm literally just moving the height of the function. So all of the x values stay the same. So all of my x values from the previous table are going to carry over. But this time, I'm going to add 3 to my input. So I'm going to add 3 to my output. So originally my output was 1 in the parent function. This time I'm adding 3 to it to get 4 as my new output. Okay. My original output for 0 was also 0. I want to add 3 to it to get my new output of 3. Same thing here. My original output for 1 was 1. Add 3 to it and get 4. My original output for 2 was 4. Add 3 to it, and I get 7. Okay, so these are my new transformed points. -1, 4, 0, 3, 1, 4, 2, 7. Same idea with subtracting 2. I'm going to keep the inputs the same as the parent function inputs, right? Because this vertical shift isn't affecting the x values at all. But now I'm going to take the original outputs of my parent and I'm going to take away 2 from them. So let's write my original outputs first. And then I'm going to take away 2 from each of these. So I get -1, -2, -1, and 2. So these are my new outputs for this transform function. So let's take a look at what these 3 graphs look like on Desmos. So here in blue, we have our parent function, just our basic boring function. In green, we have the function shifted up by 3 units. And we can see what's happening to the points that we chose. So in the parent function, we chose the points -1, 1. So maybe right here. We also chose 0, 0, 1, 1, 2, 4, and that's it. So look at what's happening to these points. With the green function, when we shifted up, we changed, the -1 stayed the same, but we moved up 3 units to get to this guy right here. So we literally moved up 3 units to get that new point. And same thing for the rest of these guys. We're literally just shifting this thing up 3 units. So there's our points, and then we have 2, 7, which is right here. Okay, and then with our red graph, we're shifting it down 2 units. All of the points get shifted down 2 units. So, originally, I had -1, 1 for my parent graph, but my red graph, I'm shifting down 2 units, so I'm going to have -1, -1. So we can see here that this guy is shifting down 2 units. This point is literally moving down of a height of 2. Then we have 0, -2. Then we have 1, -1. And finally we have 2, 2. All right. So hopefully you guys are able to visualize this a little bit better now that we have a graph. And the shifting that's taking place, we're literally not changing the shape at all. We're just picking the blue graph up in the green case, and then in the red case, we're picking it up and moving it down. All right, cool. All right, so that was vertical shift. So let's talk a little bit about horizontal shifts. So horizontal shifts moves a graph from left to right, and these shifts are a little bit counterintuitive because, and I'm going to try to attempt to explain why this is. When we have the minus sign in there, that means we're actually shifting to the right. Whereas your brain wants to shift it to the left because it's negative, it's actually shifting to the right, okay? So that's, a very common mistake that people make here. So a -2, we're shifting to the right 2 units. On the other hand, a positive moves to the left. So we're shifting this thing horizontally to the left 3 units. And it's just like a vertical shift. We're literally not changing the shape of the function. We're just picking it up, and we're either moving it to the left or to the right. Okay, so let's go ahead and get our parent graph. So I'm gonna again consider x squared as our parent graph, and for my outputs I'm gonna have the same thing here. -1 squared is 1, 0, 1, and 4. And then so the idea here, okay, so if we have a parent graph x squared and we want to move it and we want to move it this way. We just literally want to take it and shift it over. Are the heights going to be the same or different for this shifted graph? If we literally pick it up and move it to the right, are the output values going to be any different? Well, no, the heights aren't going to change. We're just moving it. We're pushing it over to the right, so there's no change in the y values, which means that the y values, since the shift isn't affecting y, those y values are going to carry over. This is only affecting the inputs. Now, I want to see, so I'm going to attempt to explain why the negative means shift right. Okay, so let's just consider this first point, -1, 1. Now, in our new point, we want to make sure that, whatever we're inputting here equals -1, right? Because if that's the case, then I'm going to get the same exact output of 1, right? And this is what I'm inputting. I'm not inputting just x. I'm inputting x minus 2. So x minus 2 had better equal -1 in order for me to get an output of 1, right? So what I do here is I say, okay, well, this input x minus 2 had better equal the input of -1, because if I put in the same input, I'm going to get the same output, which is exactly what we want. So right here, what I'm going to do is I'm going to isolate x by adding 2 to both sides. And when I do that, I get -1 plus 2, which is equal to x equals 1, right? So this is the input that I need to get this output. That is the input I need. And look, what happened to the input? Did it go to the left 2 units? Well, no, -1 to 1, you hop over to 0, right 1, you hop over to 1 from there, right 2. So we're actually shifting to the right 2 units. Okay, so that's the idea here. We want our new input to equal the old input. And that gives us, when we solve, we get our new input, which is 1. So let's do the next one. So we want our new input, x minus 2, to equal our old input, which is 0. Adding 2 to both sides, we get x equals 2. So I shifted from 0 to the right 2 units to get x equals 2. All right, same thing with the next one. X minus 2 had better equal 1 to get an output of 1. Adding 2 to both sides, I get x equals 3. So I shifted 2 units to the right to give me x equals 3. And finally, x minus 2, and you can see the pattern here. The next one has to be 4, right? Because we're increasing by 1. X minus 2 has to equal the input 2. Adding 2 to both sides, we get x equals 4. So I shifted the x value 2 units to the right to give me the new x value of 4. All right, so these are my new x values. And again, the y values aren't changing. So let's look at this other shift. So we shifted to the right here. We shifted all the x values 2 to the right. Let's look at this guy. And this time we're shifting all of the x values 3 units to the left, but we don't want our outputs to be any different from the parent function. So the parent function's outputs are again going to be the outputs here, but our x values are going to shift. So we can either, we can do that trick again. We can say, well, the input here is x plus 3. Whatever I'm squaring is x plus 3. And I want that thing that I'm squaring to equal 1, right? So I know that when I square -1, I get 1. So that x plus 3 should equal -1. All right, so I'm setting x plus 3 equal to my first x value in my parent function. Solving for x, I get x equals -1 minus 3, which is -4. So that's my first x value. All right, next one, I want the thing that I'm squaring, x plus 3, to equal 0, because I know that when I square 0, I get the proper output that I'm looking for, which is 0. Now, if I subtract 3 from both sides, I get x equals negative 3. And I'm just going to continue the pattern, right? Because I'm increasing by 1 again. So this guy should be negative 2. This guy should be negative 1. And you guys can check that by doing x plus 3 equals 1 and x plus 3 equals 2. But so this is our new, these are our new values for our tables here. So let's take a look at what this looks like on Desmos. So in blue, again, we have our parent function y equals x squared. In green, we have the shifted to the right 2 units. And in red, we have the parent function shifted to the left 3 units. Notice that the shape of the graph, the y values, are not changing at all. It's just the x values that are moving. So let's label our points just like we did in the previous problem. So in our blue parent function, we have the point negative 1, 1, which is right here. Then we have 0, 0. Then we have 1, 1. Then 2, 4. Okay, and then these points are going to start shifting. So with the green, we had negative 1, 1. Well, that turned into 1, 1. I should have done that in green. Let's do that. Let's do that again. I like being color-coded here. So we had negative 1, comma 1. That's what we had in our parent function, and that thing transformed to 1, comma 1. So we can see it. You can see it right here. This guy, negative 1, 1, moved here. So we literally picked this point up and moved it to the right 2 units to get that new point. And same thing for the other ones. So we have 2, 0. So 0, 0 became 2, 0. So this guy moved over 2 units to the right to become that guy. 1, 1 became 3, 1. And finally, 2, 4 became 4, 4. And we can see that right here pretty easily. All right. So those are those points. Let's put the same points on the red curve. First of all, we have negative 1, 1 became negative 4, 1. So you can see this guy moved to the left 3 units. So all these points are moving to the left 3 units. Negative 3, 0, negative 2, 1, and negative 1, 4. All right, cool. So hopefully you guys are seeing how the 4 points on the parent curve are moving to the right 2 units in the case of the green one, and to the left 3 units in the case of the red one. All right, so let's talk about something new. We're going to talk about what's known as vertical stretches and compressions. So a stretch, when you stretch something vertically, imagine you have some silly putty. This is a silly example, but imagine you have some silly putty and you're pulling it from both ends vertically. What's happening to the silly putty? Well, it's getting skinnier, right? So a vertical stretch means the graph is getting skinnier. And a vertical compression is it's saying that the graph is getting fatter vertically, if you will. So when we stretch something vertically, like silly putty, it gets skinnier. When we compress it, it gets fatter. All right. So the way that we denote a vertical stretch, it's the coefficient in front of the function. So if our parent function is x squared, that number that's being multiplied in front is the stretch or compression factor. So, so the vertical stretch here is 2. On the other hand, if we have a number between 0 and 1, or the absolute value of 0 and 1, we have a compression. So 1/2 is smaller than 1, and so this thing is going to be fatter than the parent function, and it's going to be fatter by a factor of 1/2. And here's the rule. So here is the rule right here, which tells us if it's a stretch or a compression. So this guy is the compression or stretch factor, and it says, hey, if the absolute value of that number that's being multiplied in the front is bigger than 1, it's a vertical stretch, just like in this example here. 2 is bigger than 1. The absolute value of 2 is bigger than 1, so that's a stretch. If the absolute value of that number is between 0 and 1, so if it's negative, we don't care. We're just looking at the absolute value, okay? If the absolute value of that is between 0 and 1, it's a compression. So in our example here, 1/2 is bigger than 0 but less than 1, so it's a compression. So let's take a look at this in action with our tables. So again, I'm just using that boring parent function x squared, and I know how to fill out this chart here. It's going to be 1, 0, 1, and 4, just like it was before. And vertical stretches and compressions don't affect the input in any way. We're taking the output of a function and we're multiplying it by some number. So what I'm trying to say here is the inputs aren't affected. So in both of these tables, our x's, our input, should be exactly the same as the parent function. The only thing that's going to change is our output, and the output is just, we're taking the output of the parent function and we're multiplying it by the stretch or compression factor. So for this one, we have a parent function output of 1, and we're going to multiply it by my stretch factor, which is 2. So my new output is 1 times 2, 2. Same thing for the next one. 0 times 2 is 0. The next one is 1 times 2. So I'm just taking my outputs of my parent function, multiplying them by 2, and seeing what I get. So 1 times 2 is going to give us 2. And 4 times 2, so my last output is 4. 4 times 2 is going to give us 8. So these are my new output values. So same x's, higher y's, silly putty stretching. Okay, think of it like that. All right, for the next one, we're going to do the same process, except this time we're compressing, and we're still going to multiply by 1/2. So the output values are shrinking when the x's stay the same. So the net result of that is that the graph is getting fatter. All right, so let's do it. So first output value of the parent is 1. 1 times 1/2 is 1/2. Second is 0. 0 times 1/2 is 0. Third one is 1. 1 times 1/2, again, is 1/2. And finally, our output for 2 in our parent function is 4. And so 4 times 1/2, 1/2 of 4 is 2. So there it is. There's our new output values. Let's take a look at this on Desmos. Okay, so my 3 graphs here, and I did the little color coding again. Blue is my parent graph. Green is my vertical stretch. And red is my vertical compression. You can see that compared to the blue graph, the green graph is skinnier. Okay, that's how we're seeing the vertical stretch. Remember, we're stretching that silly putty to make it skinnier. The red graph is fatter, right? So the red graph is a vertical compression. So you can imagine like squishing something together vertically. and it's going to get fatter. So that's the idea here. We can follow the points just like we did before. So I'm going to plot my key points on my parent graph first, which is -1, 1. So let's do that. I just want to make sure you guys really see what's going on here with these points and how the points are moving. Then we have 0, 0, 1, 1, and 2, 4. So those are our basic 4 points on our parent, and let's see how they're moving in the green. So with the green we have -1, 2, -1, 2, 0, 0, 1, 2, 2, 8. Okay, so do you see what's happening here? So the black dot is literally being it's not exactly being shifted, but it's being multiplied by a factor of 2, and so it's increasing by a factor of 2 in each case. Here we go here, and here we go here, all increasing by a factor of 2. Let's do our red points. So we have -1/2. So that's going to be right here. 0, 0, origin, 1/2, 2, 2. So we can see that this time, compared to the parent graph, the points are moving down vertically by a factor of 2. So we're shrinking this thing. Okay, so that's vertical stretches and compressions or shrinks. Let's move on to this. Okay, so let's do an example. It says, let y equal f of x. Write a formula for the transformation which both increases the y value by a factor of 6. Okay, so we know that we have a vertical stretch by 6 because we're affecting the y value by a factor. All right, so we have a vertical stretch by 6, and then it says it shifts the graph left by 2 units. So we have a horizontal shift left by 2 units. Now, we're not really sure what the function would be. Just for simplicity's sake, let's pretend that the parent function is x squared. Let's just pretend that, okay? Now, if we were to apply a vertical stretch to x squared, we would simply multiply x squared in the front by 6. And if we were to apply a horizontal shift left, we would simply apply +2 to the input value. So what this would look like if I apply, and again, left means plus, okay? So everything that's happening inside the parentheses is opposite of your intuition. Everything that's happening on the outside of the parentheses with your output goes with your intuition. So like with the vertical stretch, you're imagining, okay, it is stretch because the number is larger than 1. Vertical shifts, plus goes up, minus goes down. But with the inputs, it's the opposite of what you think. So with this, we're going to take 6 and multiply it by the output of the function. Now, the output of the function, we have to shift the function to the left by 2 units. So that says take my input and add 2 to it. Okay, so this is what my function looks like in the case of x squared. But we're not really given that it's x squared. We're just given that it's f of x. So we can apply the same logic to this guy, right? So the same logic is saying, well, hey, I'm going to change this to 6 times f of, well, whatever my input is. In this case, I'm taking my input and I'm shifting it to the left 2 units. So this right here is my answer. stretch by a factor of 6, move 2 units to the left. So that is going to be my answer in this case. Okay. All right, so let's talk about horizontal stretches and compressions. So I told you guys whatever is happening to the input is what the opposite of what you think is going to happen. So let's take a look at this. So horizontal stretches and compressions, we're multiplying a number by the input value this time, whereas before we were multiplying on the outside for vertical stretches and compressions. Here we're multiplying on the inside for horizontal. So whatever the number that's being multiplied by x's is going to tell you whether it's a horizontal stretch or shrink. So if that number that's being multiplied, and I wrote it right here, if that number that's being multiplied is less than 1 but greater than 0, if the absolute value is less than 1 or greater than 0 in this case right here, because that's 1/2, then we have a horizontal stretch by a factor of 1 over that number. So in this case, our b is equal to 1/2, and 1/2 follows the second rule down here, so it's a horizontal stretch, and the factor of it is going to be 1 over 1/2. Well, we know what that is. 1 divided by 1/2 is 1 times 2 over 1, which is 2. So that means it's a horizontal stretch by a factor of 2. Opposite of what you would think, right? Because 1/2 is between 0 and 1, but it's a horizontal stretch, and the factor is going to be the reciprocal of that number that we're being multiplied by. On the other hand, in this first case, right here, if the number that we're multiplying x by is bigger than 1, such as right here, that's 2, bigger than 1, well, then we have a horizontal shrink by a factor of 1 over b. So in this case, we have 1 over 2 is my factor of shrinkage. You can also call this compressions. I use those words interchangeably, shrink and compression. They mean the same thing. So here I have a horizontal shrink by a factor of 1 over 2. So it's always opposite of what you think. And this is only affecting the inputs, right? So when I make my little t-chart, okay, so I'm going to continue this pattern of using the parent function x squared. We'll look at some other ones in a few slides, but when I introduce this stuff, I really like x squared because I think it's one of the simpler ones. Let's fill this out first with our outputs. And then the idea here is that my outputs are going to stay the same, again, because talking about horizontal compressions and stretches only affects x, not y. So the outputs all stay the same. But my x's are going to change. And I have to multiply by the factor. I don't multiply by the number that's in front. I have to multiply by the factor. So you're multiplying by, whatever is the reciprocal of that number. So in this case, we're going to do the input is -1, right? First input is -1 times the stretch factor, which is 2 over 1, 2. So that's just equal to -2. Maybe I should make some room here. Let's do this. -1 times 2 is -2. So when I have an input of -2, I have an output of 1 in the function 1/2 x squared. All right, same thing here. We have x is 0, 0 times 2 is 0. When x is 1, 1 times 2 is 2. When x is 2, 2 times 2 is 4. So those are my new inputs. And then for this guy, Instead of multiplying my x values by 2, you're going to do it by the opposite, or the reciprocal, which is 1 over 2. So original input of -1 times 1 over 2 is -1/2. Followed by 0 times 1/2 is 0. 1 times 1/2 is 1/2. And 2 times 1/2 is 1. All right. Okay, so those are my new input values, the one that I circled. So let's take a look at what this looks like on the graph. Now, something cool about this is that vertical stretches and compressions are can be related to horizontal compressions and stretches. So like, if you were to expand this guy out here, if you were to square 1/2 x, what you would get is a 4th x squared, right? 1/2 x times 1/2 x is a 4th x squared. And notice this is a vertical shrink, right? A vertical shrink by a factor of a 4th, but we can also look at it as a horizontal stretch. Horizontal stretch and vertical shrink are the same ideas, right? Because we're making the graph fatter in both cases. A horizontal stretch means we're making the graph fatter. Okay, so anyway, enough about that. Let's look at the graphs here. So plotting my basic points for the parent function. Let's do that. -1, 1, 0, 0, 1, 1, 2, 4. And then let's take a look at our new x values for 1/2 x squared. So now we have -2, 1. So that's right here. 0, 0, 2, 1, 4, 4. All right. So horizontal stretch. We're stretching the points horizontally, as you can see here. And the graph looks fatter than the parent graph. Let's look at the other one, which was 2x squared. Again, you can look at this as 4x squared. That's a vertical stretch by a factor of 4. So this graph should look skinnier, right? So it's a vertical stretch by a factor of 4, but it's also a horizontal shrink by a factor of 1/2. Okay, so you can look at it in two ways. All right, so we have -1/2, 1. Oops. So that's going to be that point right there. 0, 0. 1/2, 1. And 1, 4. Okay, so you can see from the parent graph, the points are shrinking horizontally. They're getting closer and closer to each other horizontally. Okay. All right, so that's horizontal stretches and shrinks. Okay, so this is a summary of everything we talked about, and I have some letters here representing the various transformations that we just went over. So A is going to be that vertical stretch or compression. B is the horizontal stretch or compression. Notice that it's factored out here. That's going to be important in just a little while, so just take note of that. C is the vertical shift, and C is the horizontal shift, and D is the vertical shift. So let's go ahead and use this to identify transformations here. All right, so let's do some examples here. So notice that to the right, I have our little, our basic formula here, or a basic equation. Okay, so let's take a look at our first function. We have y equals a half times the square root of x minus 6 plus 1. Now, what is the very basic parent function that we are comparing this to? We're trying to transform a very basic parent function into this. So the parent function, if we look at our list over here, which one looks closest to what we have? Well, it has to be the square root function, right? Because we have a variable under the square root. So let's go back here, and we're comparing. So our parent function is going to be just simply y equals the square root of x, right? And so we're trying to see, hey, what transformations are taking place to get from here to here, all right? So let's take a look first. Do we have an a? Do we have a number that's being multiplied on the outside of the function? Well, yeah, we do. We have this 1/2 right here. Now, if the 1/2 was right there, then that would be a b value. That would be something that's affecting the graph horizontally. But since it's on the outside, that's going to be a vertical compression, right? Because the number is between 0 and 1. And so we have a vertical compression of a half. So that's our a value. Now, the b value, we don't have a number multiplied by x. It's just 1, so we don't really have a horizontal stretch or shrink. But we do have a c value here, right? And so what the minus says is, hey, we're shifting this thing to the right, and we're shifting it to the right 6 units. Notice that the minus 6 is under the radical, just like this x is under the radical. So that's part of our input value. If the minus 6 was on the outside where this plus 1 is, then it would be a vertical shift. But it's on the inside of the radical, so this is going to be a horizontal shift right. Again, it's opposite of what you think with the horizontal, 6 units. Okay? And finally, we have this plus 1 on the outside of the radical. So it's saying, hey, take the output of whatever this function is and then add 1 to it. So that's going to represent a vertical shift. So this is going to be a vertical shift up 1 unit. And we can compare these two on Desmos if we want. I think I will do that in this case. So let's see, we have 1/2. Well, yeah, why not? Let's do this. Let's put it on Desmos. All right, so let's put our parent function on here. We have the square root of x. And then our transformed function is 1/2 times the square root of x minus 6 plus 1. All right, so there it is. So we have so let's actually make this red and make this blue just to stay consistent with our colors. I always made blue the parent function. So what do we have here? We have a vertical compression of a half. We have a shift to the right 6 units, and then we have a shift up 1 unit. All right. So that is the idea here. Now, if you just look at this graph, it doesn't look like the red graph is shifted up 1 unit from the blue graph, does it? Well, that's because there are other factors in play here. There's a vertical compression going on, right? And that's what is causing this thing to be closer to the x-axis than it would be normally. If we got rid of, let's see what would happen if we got rid of the vertical compression. If we got rid of the vertical compression, well, then that makes a little bit more sense, right? We're shifting over 6 and we're adding 1 to it. So, these transformations work together to make the entirety of the graph. is the point I'm trying to make here. All right, cool. So those were the transformations for that guy. Let's look at number 2. So what is the parent graph of this? What does this most closely resemble out of our parent graphs here? Well, it's squared, so it has to resemble the quadratic, right? Let's go ahead and compare this to the parent function x squared. So our parent function here is going to be y equals x squared, right? Because we have the square here, we have a variable here. Let's compare it to x squared. Now, what's important here is something that you need to be careful about, okay? So pay attention to this, is what's happening on the inside. We want to make sure this coefficient of x is 1 before we can say anything about shifting and stretching, all right? Because right now, doesn't it look like it's shifting forward to the left? Yeah, it does. Well, that's not the case because we need to have it in this form to appropriately define the horizontal shift. So I'm going to rewrite this. I'm going to rewrite this as y equals 3. That's fine. And now what I'm going to do, to put it in this form, I'm going to take the 2 out. I'm going to divide both 2x and 4 by 2. And when I do that, what I'm left with on the inside is x plus 2. So it's actually shifted to the left 2 units, not 4 units. I wanted to make that very clear. And so this is in this form. I think we're good. You can always check that you did this right by distributing back in and seeing if you get what you originally had, which we do, 2x plus 4 when we distribute that back in. All right, so let's go ahead, since we're in the proper form now, let's identify our transformations. Well, first of all, do I have an a? Yes, I do. I have a number that's being multiplied on the outside of the function, and that's 3. So I have a vertical, since 3 is bigger than 1, it's a vertical stretch by 3. Looking on the inside, I have a horizontal shift to the left 2 units. This is a horizontal shift left by 2. I also have a horizontal compression. Right, this guy is going to tell me, since it's always opposite what you think, right? 2 is bigger than 1, and so this is a horizontal compression, or shrink, if you like that better. And it's going to be a compression by 1 over 2, so the reciprocal of 2. And finally, do we have a vertical shift? Do we have a d? Well, yeah, we do. We have minus 5 at the end of this function. So this is going to be a vertical shift down 5 units. All right, so those are our transformations for this guy. Let's take a look at one more. So what would the parent graph for this guy be? 5, absolute value of 1/2 x minus 2. Well, it's got to be the absolute value function, right? Because we have an absolute value, the other ones don't. So our parent function is just going to be simply the absolute value of x. Okay? And so what are the transformations that are taking place here? Well, the first thing I want to do is I want to get this into the proper form because I noticed that the coefficient of x isn't 1, and I need it to be 1 to talk about the shifts. So the first thing I want to do is I want to factor out that 1/2 on the inside of this absolute value bar. Right? I'm just dividing 1/2 x by 1/2 and also -2 divided by 1/2. So -2 divided by 1/2 is just -2. When I divide by a fraction, I multiply by the reciprocal. So that's -4. And again, distribute this back in. See if you get this. You do. And if you don't, try again. I don't know. Okay. All right, cool. So this is the form that we're going to be looking at here. And let's take a look at our transformations. Well, do I have a number multiplied in the front of the absolute value? Well, yeah, I do. I have this 5 right here. So that's going to be my vertical stretch factor. So I have a vertical stretch by a factor of 5. Okay. Looking on the inside now, so what's affecting horizontally? Well, I have a shift, right, because I have that -4. So this is going to be a horizontal shift right by 4 units. And I also have a horizontal stretch because of this number right here. This number that's being multiplied by x minus 4 is going to be my horizontal stretch factor. So this is going to be a horizontal stretch. Again, it's opposite of what you think. Vertical is exactly what you think, but horizontal is opposite. So this is going to be a horizontal stretch by a factor of not 1/2, but the reciprocal of 1/2 by 2. All right, so those are my transformations there. Hopefully this made some kind of sense. So let's do some more problems here. Before we do that, we're going to talk about 2 more transformations. We talked about shifts, we talked about stretches and compressions, both vertically and horizontally. The next thing we're going to talk about are reflections. So algebraically, a reflection across the x-axis is indicated by a negative on the outside of the function. Okay? So like for example, if I have the parent function x squared, well, if I put a negative in front of the x squared, that means, hey, I'm going to take x squared and I'm going to use the x-axis as a mirror. And what I get when I reflect x squared over the mirror, I get negative x squared. So you can kind of see what I'm talking about here as the x-axis being the mirror, right? So that's all that is. That's the mirror image. So the negative is on the outside of the function, which means that we're applying this to the output only. So what does that mean? Well, that means for the parent function, the inputs of the parent are going to be the same inputs as the reflected function. Now, the only thing that's different is that I have to multiply by that -1 that's in the front with my outputs. So my outputs for my parent, again, are 1, 0, 1, and 4. And for my reflected outputs, I have 1 times -1 is equal to -1. 0 times -1 is 0. 1 times -1, again, is -1. And 4 times -1 is -4. So I'm just multiplying my outputs by -1. And we can see this on the graph too. If I plot my my points here, and actually this is not a great graph. Yeah. But the idea is that the inputs are the same, but the y values are opposite. And we can see that, if we just look at, let's say, this point right here, and compared to this point right here, you see the x values, they're in the same place horizontally, but they're in complete opposite places vertically, and that's what the negative sign is doing here. All right, so those are reflections across the x-axis. Let's take a look at reflections across the y-axis. So this time, the negative is being multiplied by the argument or the input value, right? So it's not on the outside this time, it's on the inside of the function being multiplied by x. So let's take a look at our inputs and outputs here for this function x minus 3 squared plus 5. Well, if I plug in 3 for x, I get 0 plus 5 is 5. Plug in 4 for x. I get 1 plus 5 is 6. Plug in 5. 4 plus 5 is 9. All right? So this time, my y values are not being affected, right? Because I'm multiplying on the inside by my input values. So what's being affected is the x values here. And I simply multiply my x values by a -1 because here the difference between this guy and this guy is just multiplication by -1. So here I have 3 input of the original times -1. So my new input is -3. And then I have old input times -1. So my new input is -4. Old input 5 times -1. New input is -5. All right. And we can see this on the picture. This time, when we have a reflection across the y-axis is acting like the mirror here. So this guy on the left, when he looks into the y-axis mirror, he sees this guy, right? And, if this guy on the right looks in the mirror, he sees this guy. So that's the idea here. Reflecting across the y-axis, we're multiplying the x value in the argument by -1. So let's do some examples here with all of these transformations combined. So it says, how is this function and this function related? Well, they look almost the exact same, except the difference that I notice is this negative in the front is not there in the first one, and this +1 is also not there. And so that negative in the front, that's being multiplied by the function. So this is telling me that I have a reflection. That negative is telling me I have a reflection across the x-axis. And again, we're not comparing this to the parent function. That's why I'm not talking about 2 or 3. We're just comparing this to the original function that we're given, not the parent function. So reflection across the x-axis, and also this +1 is telling me that I have a vertical shift up 1 unit. All right, so those are how those are related. Let's take a look at number 2. I have ln of 8x and ln of -8x. So what's the difference between the second one and the first one? Well, the only difference is this negative right here. And is the negative on the inside or the outside of the function? Well, it's on the inside. So that means that's a reflection across the y-axis. And that's the only difference between the two, is that negative. So we have a reflection across the y-axis. All right. Let's look at we have some, I graphed these guys on Desmos for you. So again, looking at number 1, what did we say the transformations were? We said it was a transformation, a reflection across the x-axis, and a vertical shift up 1 unit. So we can see that is the case for the green and the blue function. The x-axis is acting like the mirror here, and we're also shifting this thing up 1 unit once we reflect it. And the second one, we can see here that my original function, ln of 8x, and my transformed function, ln of -8x, well, these are just reflections of each other across the y-axis. This time the y-axis is acting like the mirror. All right, so those are some examples. So let's actually talk about steps to transforming a function. We're going to do a bunch of examples with these, so don't worry. We're going to make a table for the parent function. That's our first step. And then, and actually I should say for the, well, no, let's keep it like that. All right, so that's our first step. Then we're going to set the argument of the new function equal to each x value in your table, and those are the new transformed x values. So what do I mean by argument? I keep saying that word, but I don't know if I've defined it for you guys yet. The argument is anything that is in your input space. So for example, if we have y equals, let's say 3 times 2x minus 1 squared plus 1. The argument is going to be everything in our input space, which is 2x minus 1. That's the thing that's being squared. So it's, what would originally be squared in your parent function. So 2x minus 1 is the argument. (2x minus 1 is the argument. Let's look at another example. What if I have an exponential function? How about 2 to the 3x minus 4? What's the argument here? Well, the original parent function is 2 to the x. And what would go in that x, the x place, is 3x minus 4. So that would be the argument here. So that's what I mean by argument. And we're going to do a bunch of examples with this. So that's what we're going to do first. We're going to set the argument of the new function equal to the x values in the parent function. And those are going to be our new x values. And lastly, we're going to figure out what our new y values are going to be by multiplying the parent function's y values by the stretch or shrink factor and then applying the vertical shift to that. So let's just get into it and do some examples here. We have if f of x equals 2 raised to the x, sketch the graph of negative f of x. Well, just based on this transformation, what is the transformation going to be? Well, since the negative is being multiplied on the outside, this is a reflection in the x-axis. So this is a reflection across the x-axis. All right. So the first thing I'm going to do is I'm going to make a table for my parent function here, which is 2 to the x. Just a brief little table here. And I'm just going to pick some random points, some nice easy points to work with. How about -1, 0, 1, and 2? That seems like enough. Well, if I plug in -1 to x, I get 2 to the -1, which is a half, right? 1 over 2 to the 1. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the second power is 4. So these are my y values for my parent graph. Now I want to look at my transformed graph. Now notice that I don't have to do anything with the x values because that negative is on the outside of the function. So negative f of x is simply -2 to the x, right? That negative multiplied by f of x. So with that being said, the x values are going to be the same, but this time the y values are going to be multiplied by -1, right? That's what we're doing. And you can think of it as, like a vertical. In this case, we're not compressing or stretching, but you want to think of it in the same way. We're multiplying by -1. So here we have a half times -1 is -1/2. 1 times -1, I'm just taking the outputs and multiplying by -1. 2 times -1 is -2. And 4 times -1 is -4. All right, cool. So we have these graphs, and let's do a quick sketch of the parent graph and the transform graph on the same plane, on the same, the same plane. Okay. So let's do this, and you guys know how I am. I'm very lazy with these graphs. So let's just get into it. So first of all, let's do the parent. I have -1, 1/2. So maybe like right there. 0, 1 is right here. 1, 2 right here. 2, 4. Maybe like right here. Lazy, lazy, lazy. Okay, so we know what happens with these exponential graphs, right? This thing's going to go up forever, and it's also going to approach the horizontal asymptote, which is y equals 0, because it's not shifted or anything. So that's our parent graph. Beautiful graph. I know my art skills are pretty pretty awful, but I hope you guys get the picture. So let's look at the transform graph now. So first point, we have -1, -1/2. That's going to be roughly right here. Then we have 0, -1, roughly right here. 1, -2. 2, -4, somewhere down here. So hopefully you guys are seeing that, that this thing is going to hug the x-axis just like that. Again, it's going to have the same asymptote because we're not shifting this thing vertically. We're simply reflecting it across the x-axis. So hopefully you guys can see the mirror image here. So this is y equals -2 to the x, and this is our parent function y equals 2 to the x right there. All right, let's see where we're at now. Let's look at this guy. So it says, if g of x equals x squared, make a table and graph with this transformation, -2g x plus 1 minus 3. So the first thing I like to do with problems that look like this is make it look a little familiar. I don't like this g in here. So since g of x is x squared, well, the thing is, we can get rid of this by saying, hey, g of x plus 1, I'm simply plugging x plus 1 in to my argument for g. So this is just x plus 1 squared. All right, so let me replace that here. I have y equals -2, and instead of g of x plus 1, I'm writing x plus 1 squared minus 3. So right off the bat, so this is my transformed, and then my parent is x squared. So these are the two functions that I'm comparing, and let's talk about the transformations. Well, first thing I notice is I'm multiplying by 2, and in particular -2. So this is like two transformations in one. The negative says, hey, I'm reflecting this thing across the x-axis. So that's the first thing. So reflection across the x-axis. That's the first thing that the negative tells me. And what the 2 tells me is, since it's being multiplied on the outside of the function, that's telling me it's a vertical stretch by a factor of 2. So this is a vertical stretch. Let's see where we're at on time. Cool. Let's look at and see what's happening on the inside. Well, I see a +1 in the argument. So that's telling me, hey, I need to shift to the left 1 unit. So horizontal shift left is kind of redundant, but oh well. Left by 1. And finally, this -3 at the end is saying, hey, I'm going to take whatever I get as my output here, and I'm going to shift those outputs down 3. I'm going to shift them by 3. So this is going to be a vertical shift down 3. Let's see. Okay. All right, cool. So let's go ahead and make a table for my parent function and then my transform function. So you guys know the drill. 1, 0, 1, 4. And then we're going to transform this into x. And then we have -2 x plus 1 squared minus 3. So what's happening to my x values? Well, the first thing I can do is, so make a table for the given function. We did that. Now we're on to step 2. Set the argument of the new function equal to each x value in your table. Well, the argument of my new function is x plus 1. So I take x plus 1 and I set it equal to the argument in my first table, which is negative 1. Solve for x. Subtract 1 from both sides to get x equals negative 2. Do the same thing for the next one. I have argument x plus 1 equals the next x value, which is 0. Subtract 1 from both sides, and we get negative 1. And you guys can see the pattern now, right? Negative 2, negative 1. The next one should go up by 1, which is 0. Then we have 1. Okay, so there we go. So we shifted all the x values to the left by 1. Those are our new x values. Excellent. Okay, so now what we have to do is step 3. Step 3 says, hey, multiply the y values in your parent table by the stretch or shrink factor and then apply the vertical shift. So that's what we're going to do here. We're finished with x. That's great. Now we need to take the y's. We need to look at the y's. So the first y we have, we're going to multiply by that vertical stretch or shrink, which is negative 2. And then we're going to apply the negative 3 after that. So this is going to give us a net result of negative 5. That's our output here. All right, same thing with the next one. We have an output of 0. We're going to multiply it by that vertical stretch factor, negative 2. Then apply the vertical shift, minus 3, and we get minus 3. Here, our output is 1. 1 times negative 2 minus 3 is again negative 5. And finally, our last output is 4. So 4 times negative 2 minus 3 is negative 11. Okay, so those are my new function values, and we can go ahead and just do a rough sketch. Just a rough sketch here. So first, my parent function, I have negative 1, 1, 0, 0, 1, 1, 2, 4. So it's going to look something like this. And then for my transform function, I have negative 2, negative 5, negative 1, negative 3, 0, negative 5, and 1, negative 11. So something like this, roughly something like this. So we can see that it's skinnier, so we can see the vertical compression of 2. We can also see that it's flipped over, so we can see that reflection in the x-axis there. We can also see that it shifted to the left 1 unit and down 3 units. So those are my parent functions. So y equals x squared, and then y equals negative 2x plus 1 squared minus 3. Okay, so for this problem, we're going to take a look at e to the x as our parent function, and we're going to graph some reflections here. So the first thing is f of x equals e to the x. So this is just e to the x. And I'm going to make a table, but I'm also going to use Desmos to show you guys this just to save some time with the video. Okay, so if I make a table for e to the x, I have x as my input, e to the x as my output. Let's take negative 1, 0, 1, 2. Plugging this in, I have e to the negative 1, which is 1 over e. E to the 0 is 1, e to the 1 is e, and e squared, well, that's just e squared. And this is going to give me some approximate numbers here. So 1 over e is approximately 0.37. E is approximately 2.7. And e squared is approximately 7.4. Okay, so this is our first graph here. And we look at it on Desmos. So we have e raised to the x. And there it is. All right, so let's look at our next one. So our next one, we have negative e to the x. So the negative is being multiplied on the outside, which means that this is a reflection in the x-axis. So this is a reflection across the x-axis. And we can get a table for this going. So our x's are going to be the same as our parent function. And again, I'm just multiplying this negative on the outside of e to the x. The x's are going to be the same, but the y values are going to have a negative attached to them. So negative 1 over e is approximately negative 0.37. Negative 1. Negative e is approximately negative 2.7. And then negative e squared is approximately negative 7.4. So these are some ordered pairs. Let's take a look at it on Desmos. So let's do negative e to the x. And let's make this red. All right, so we can see what's going on here. This red is a reflection of e to the x across the x-axis. We can see that the x-axis acts like the mirror there. And let's take a look at our next function here. So we have, the next one is going to be f of negative x. Now the negative is being multiplied on the inside, so this is a reflection across the y-axis. Okay, let's get a table going. So this time, the output values of the parent function aren't being affected because the negative is being multiplied by the inputs. So if I plug in negative x into e to the x, I get e to the negative x. All right, so that's what this function looks like here. And as I said, the y values are going to stay the same, so I have all of these same y values, 0.37, 1, 2.7, and 7.4. But my x values are all going to be multiplied by negative 1. So negative 1 times negative 1 is positive 1. 0 times negative 1 is 0. 1 times negative 1 is negative 1. And 2 times negative 1 is negative 2. So these are some ordered pairs for this function. So let's take a look at it on Desmos. So we have e to the negative x. This should be a reflection in the y-axis. There we go. Let's see if we can turn it yellow. I'll turn it orange, close enough. Yeah, so our blue parent function and the orange function are reflections across the y-axis this time. And let's look at our final example here. So this time we have both reflection in the y and reflection in the x. So what does our function look like? Well, it's negative e to the negative x because I'm multiplying the negative 1 on the outside of e to the x, and I'm also multiplying the x by negative 1 on the inside there. So that's what my function looks like, and I'm going to multiply my parent function's outputs by negative 1 and also the parent function's inputs. So all of these are going to be negatives of each other. So 1, 0, negative 1, negative 2. And then for my outputs, negative 0.37, negative 1, negative 2.7, and negative 7.4. So let's take a look at how this looks on Desmos. Let's make it green. And there it is. So that is a reflection across the x-axis and a reflection across the y-axis. Okay, so that is that example. Let's take a look at this one. Okay, so it says we have this function y equals f of x. We know it contains the point 2, 4, and it says what point must lie on the graph if it's reflected across the x-axis and if it's reflected across the y-axis. These are two separate questions here. So, well, we have this point 2, 4, and if it's reflected across the x-axis, that means the x value is going to stay the same, but we're going to multiply the y value by -1. So we know that this point had better be on there if it's reflected across the x-axis. On the other hand, when we reflect across the y-axis, well, now the y value of the parent point stays the same, but we multiply the x value by -1. So this is going to be -2, 4 is our answer for part B. Okay, so it says give a formula for the transformation v of -x minus 2 if v of x is equal to x squared minus 3x minus 1. And it says then graph both the function and the transformation. So first of all, v of -x. Well, v of -x, we're just plugging in -x in anywhere we see an x in v. So v of -x is going to be -x squared minus 3 times -x minus 1. And then minus 2 I can just simply add at the end of this. So let me actually write that out here because we have this minus 2 up here. So that's minus 2 on the outside. And then I can simplify this. So -x squared is the same thing as positive x squared, right? -1 squared is positive 1. -3 times -x is a positive 3x. And then -1 minus 2 makes a -3. So this is v of -x minus 2. This is the formula for it. And we also have a formula for v of x to consider. We have x squared minus 3x minus 1. So we want to get t-charts for both of these. So the parent function is just v of x. So we have x, and then we have, maybe I'll do this in blue to stay consistent with the parent function before the transformations. So let's do x, and then we have x squared minus 3x minus 1. So the first thing is the negative x. So that's, well, let's pick some values first of x, plug them in, and then see what happens. How about -2, -1, 0, 1. Okay, so when x equals -2, I'm just plugging it into the function -2 squared minus 3 times -2 minus 1. It's going to be 4 plus 6 minus 1 equals 9. So we have -2, 9. Next, we have -1 squared minus 3 times -1 minus 1. And that is going to give us 1 plus 3 minus 1 is 3. All right, so there is my regular function. And so for my transform function, it's saying, hey, I'm going to multiply all of my x values by -1, and then I'm going to subtract 2 from all of my y values. So my transform function, I have x, and then I have x squared plus 3x minus 3 is my transform function. So with my x's, I'm multiplying all of those by -1 in my parent. So I have 2, 1, 0, -1. And then for my y's, I'm just taking the original y's, 9, 3, -1, -3, and I'm subtracting 2 from them, right? Because that's on the outside of the function. So -2, -2, -2, -2 is equal to 7, 1, -3, and -5. So these are my outputs. And what I'm going to do is I'm just going to use Desmos to look at this. Okay, so there's my parent. And there's my transform function. Okay, so reflection in the y-axis and a shift down 2 units. That is our, so that is going to be our function here, our transform function. And what you can do is you can make sure that all of these points that we got are actually on both the parent and the transform. So like -2, 9, -1, 3, 0, -1, 1, -3. So these should all be on our parent function. And then for our transform function, we should have the points 2, 7, 1, 1, 0, -3, -1, -5. So I encourage you to use Desmos to verify that these points are indeed on the parent graph and the transformed graph respectively. Okay, the graph of h of x contains the point 4, 16. Find a point on the graph of negative h of 1/2 x plus 3 minus 8. Okay, so what are we doing here? Well, let's go ahead and first distribute this negative to see what's happening. Now be careful here, because this whole thing in parentheses that I'm highlighting in red, this is the argument. So we don't apply that negative on the outside to the argument. We just apply it to to the front of h and also to this -8, which is not part of the argument. Okay. So here we go. I'm going to distribute that negative in first, noticing that I'm leaving the argument alone. Just trying to get rid of some parentheses here. And -1 times -8 is going to give me that +8. All right. So there's my function. So we have a function, and it contains, this parent function contains the point 4, 16. And the question is, what other point has to be on the graph given these transformations? Well, we can first apply our transformation to our x values. So what's happening to the x values? Well, everything in the argument is what's happening to the x values. So the transformations here, let's just list the transformations for x first. What we have is, first of all, with the shift is going to move the parent graph to the left 3 units. So that's the first thing. And the second thing that's happening to x, Well, this 1/2 in the front is telling me this is a vertical stretch, or sorry, a horizontal stretch. A horizontal stretch by a factor of 1 over 1/2, which is 2. All right, so that's what's happening to x. Now, what's happening to y? Well, we can see this -1 on the outside is telling me that this is a reflection across the x-axis. And the +8 at the end is telling me that I'm going to shift this up 8 units. All right, so let's apply these transformations to the point that we have here. With the x, we're going to first multiply the original x by 2 to account for the horizontal stretch, and then we're going to subtract 3 to account for the horizontal shift. So what we have here is we have 4 times 2 minus 3. And then for our output, 16, well, we're just going to multiply -1 by 16 to account for that negative in the front there. So we have -1 times 16. And then we're going to subtract, well, actually, I'm sorry, we're not going to subtract 8, we're going to add 8. We're going to add 8 here. All right, so when we do that, we get 8 minus 3, which is 5. And then -16 plus 8 is going to give us -8. So this is our answer here. This point has to be on our transformed graph of our parent function that contains 416. So that is our answer. All right, let's go ahead and look at this. So I wanted to do an example like this because you have one on your homework, and be careful at this part right here where it says enter your answer in increasing order. Okay, so that's the big thing that you should watch out for. All right, so it says the table below gives the values of a function v. Complete the following table to give 5 values of the function w of t equals 45 minus 2v times blah, blah, blah. Okay, so the first thing I'm going to do is I'm going to transform my t values, or my x values, if you want to think about it like that. Okay, so, and actually we can write this a little bit better. This 45 in the front can be put at the end with a plus sign, just to make it look a little bit more familiar. We have -2v of -0.5t, and then at the back we have a plus 45. So that looks more like our vertical shift that we're used to, vertical shift form. So I'm going to transform my t values first. So these are like acting like my x values. So what's happening to x? Or what's happening to the t values? Well, everything in the argument. So this -0.5, but remember, we're doing the reciprocal of -0.5, which is 2, right? Because 0.5 is 1/2, the reciprocal is 2. So I'm actually going to multiply all of my t values by -2. So I have 0 times -2 equals 0. 1 times -2 equals -2. 2 times -2 is -4. And 3 times -2 is equal to -6. 4 times -2 is equal to -8. So those are my t values, my new t values. And let's find the corresponding y values, so the v of t values. So we start with 28, and then 17, 21, 14, 24. So these are my outputs. So what's affecting y here? Well, we better multiply our y values by -2 and then add 45. So that's what's happening to my y values. So this is going to be 28 times -2 plus 45. Of course, I'm running out of room here. That's going to give us -11. Then we have 17 times -2 plus 45 equals 11. (21) times -2 plus 45 equals 3. 14 times -2 plus 45 equals 17. And finally, 24 times -2 plus 45 is going to give us -3. Okay, so we can write these as an ordered pair, right? So we have this one goes with -11. So we have 0, -11. So this is t, phi of t. -2, 11. So the second one goes with 11. -4, and then 3. -6, 17. -8, -3. So on Wiley, be careful when you're entering these in because it does say enter your answers in increasing order. So we want to start with the lowest t first. So the way you're going to enter this is -8, -3. Then the next lowest t value is -6, 17, -4, 3, -2, 11, and 0, -11. So that is going to be our answer there. All right, suppose we have a function f of x equals ln of x. Graph this function and the transform functions with these transformations. All right, so first of all, let's figure out what our new transform function looks like. So we know that our parent function is just f of x, or y equals ln of x. So our transform function, we need to apply these transformations. So we don't have an a value. We don't have a vertical compression. We do have a reflection across the x-axis. So what we're going to have here is y equals -ln. And then what's my argument going to look like? Well, my argument is affected the horizontal shift and the horizontal compression. So what is this going to look like? Well, this is going to look like the horizontal compression by 1/3 means that that number, that coefficient of b is going to be 3, right? It's the reciprocal. It's always opposite of what you think. And then the horizontal shift to the right 2 units is going to tell me we're going to do x minus 2 to account for the right shift. So that's my argument. We took care of this with the negative in the front. We took care of this. And the last thing is vertical shift up 3 units. So that's going to give us this plus 3 right here. Okay, so that is my my function there. So let's get some good points for my parent function. We have x ln of x. So first thing is the asymptote, right? We always have vertical asymptotes with these log functions. So when x is equal to 0, this function is undefined. So that's going to be my vertical asymptote there. When x is equal to 1, log base e of 1, well, that has to be 0. And then finally, we have another point, e1. So that's my parent function. So with my transform function, what I can do to get my new x values is I can first set my arguments, which is 3 times x minus 2, equal to these x values. Right? That was step 2 in transforming our function. So first of all, I have 3 times x minus 2. Let's set that equal to 0 first. Well, dividing both sides by 3, I just get 0 over 3 is 0, x minus 2 equals 0, so x equals 2 is going to be my new x value here. All right, let's do the next one. So we have 3x minus 2 equals my next x value, which is 1. Divide both sides by 3, I get x minus 2 equals a third. And then if I add 2 to both sides, I get 1/3 plus 2. 2 is 6/3, so that's going to be 7/3 is my second x value. And finally, for my third x value, 3x minus 2 is equal to e. Divide both sides by 3, x minus 2 equals e over 3. And if I add 2 to both sides, I just get x equals e over 3 plus 2. And I'm just going to leave that as it is for now. All right. So then with my y values, it says, hey, I need to multiply my y values by -1 and then add 3 to them. Well, multiply undefined by something and add 3, well, that's still undefined. Multiply 0 by -1 and add 3, that's going to give us 3. Multiply 1 by -1, that's -1 plus 3 is 2. So these are my new transformed values here. So let's do a quick sketch of what this is going to look like. Let's do a quick sketch here. For my parent function, I have the asymptote at x equals 0, indicated by this dashed line, then 1 comma 0, and then e comma 1. So something like this. It's going to hug that asymptote, and it's going to look something like this. Now let's do the transform function. Well, this time my asymptote has shifted over to x equals 2. So now my new asymptote is going to be right here. And 7 over 3, well, what is that going to be? Well, that's going to be about 2.3. Maybe I should write this here. And actually, let's see what e over 3 plus 2 is. So e divided by 3 plus 2 is going to be about 2.9. So this is about 2.9. So at 2.3, I have 3. And at 2.9, I have 2. All right, so these are my my points here, and so we have something that looks like, something that looks like this. Let me draw this better. So it's gonna hug that asymptote. And it's going to go down like that. All right. So that's our picture. We can always confirm this picture with Desmos. But yeah, so that's our parent function and our transform function. Okay, so we want to graph and describe the transformations for this function. So the first thing is, what is our parent graph? What does this most resemble? Well, it has a square root and a variable under the square root, so our parent function is just going to be y equals the square root of x. Now let's go ahead and make a table for our parent function. So we have x, and then we have square root of x. We can't take negative values under the radical, so let's just do 0, 1, 2, 3. All right, plugging these into x, we get 0, 1, square root of 2, square root of 3. Okay. Now, let's talk about my transformations. Okay, so what's happening on the outside is multiplication by -2. So we can sort of split this into two separate transformations. The first one is a vertical stretch by 2. And that negative sign is going to tell me it's a reflection across the x-axis. Looking at the outside, I have a +3 on the outside of the radical, which tells me that's going to be a vertical shift up 3 units. And finally, what's happening on the inside of my argument is x minus 1, is I'm shifting to the right 1 unit. So this is going to be a horizontal shift to the right 1 unit. All right, excellent. So let's actually get a table for this graph. So here I have x, and then I have -2 square root of x minus 1, and then on the outside +3. So let's first figure out what my new x values are, quote unquote new x values. I'm going to take my argument and I'm going to set the argument equal to each x value to get my new ones. So I have x minus 1 equals 0. Solve for x equals 1. Okay, next one, x minus 1 equals 1. Solve for x equals 2. X minus 1 equals 2, so x equals 3. And you guys can see where this is going. The next one should be 4. So that's what my my new x values are. So set the argument equal to each of the x values and solve for x. All right, now I need to work with my new y values. And so what I do is I apply first the stretch. So I multiply each y value by -2, and then I add 3 to them. So first I have 0 times -2 plus 3 is going to give me 3. Then 1 times -2 plus 3 is going to give me 1. Square root of 2 times -2 plus 3 is going to give me approximately 0.1716. And then square root of 3 times -2 plus 3 is going to give me approximately -1. All right, so those are my new points here. So I can graph both of these in the same plane. I can use Desmos, or I can just do a quick sketch from my table here. So my parent function looks a little something like this. It's increasing. So something like this. Here's my parent function. And then for my transform function, I have 1, 3. So maybe somewhere up here. 2, 1. 3.176, something like that. And then 4, -1. Something like this. I'm not the best at drawing these graphs, so let's try that again. So maybe it looks a little something like that. All right. Okay, so that's a rough sketch of my transformed graph and my parent graph, square root of x. Let's try another one. Graph and describe the transformations for this guy. Well, what's my parent function going to be? Since I have absolute value bars here, my parent function should be absolute value of x. This is my parent function. And let's get a table going for it. I'm going to do -1, 0, 1, 2. Remember, when I put anything in the absolute value bars, it's going to give me the positive version. So the positive version, the absolute value of -1 is simply going to be 1. Absolute value of 0 is 0, absolute value of 1 is 1, absolute value of 2 is 2. And what the absolute value graph is going to look like, it's going to look similar to a parabola, except it's going to be pointy. It's going to have that point at its vertex. It's going to look something like that. All right, so let's talk about the transformations before we make the table. The first thing I should do, I always want this number in front of x to be 1. So I need to factor out that -2 first. So when I do that, I'm left with, well, -2x divided by -2 is simply x. -4 divided by -2 is simply going to be 2, positive 2, right? And actually, I need to make this parentheses. Sorry, let's see. Let's try this again, Sarah. So we have x plus 2. Notice that when we distribute this back, we get exactly this. And I wanted to put it in this form so that my coefficient of x was 1. Right? That's when you can start saying things about horizontal shifts and stretches and so forth. All right, so that's that. And then we have the +6 at the end. So we want to look at this guy. Okay, so let's talk about the transformations. Well, on the inside, I'm noticing that I have a horizontal shift to the left 2 units. I also have a horizontal compression by a half, right? Because I take the reciprocal of 2, which is 1/2. This negative in the argument, this multiplication by a negative, is telling me it's a reflection across the y-axis. And finally, at the end here, not in my argument, is going to be addition by 6. So this is going to be a vertical shift up 6 units. Okay. All right, so let's get my transform table going. So I have x, and then I have -2 x plus 2 in absolute value bars, and then that +6 on the outside is my output here. Okay, so what's happening to my x values? Well, I'm going to be multiplying my x values by -1/2, and I'm going to be taking away 2 from them because of this guy right here. Right? It's always opposite of what you think. So my first x value that I'm transforming, well, actually, maybe let's do it like this. Let's take the argument. Let's do it how we've been doing. Let's take the argument, which is, the argument is -2x plus 2, and we're going to set it equal to the first x value, all right, and solve for x. So first thing, I'm going to divide both sides by -2 to give me x plus 2 equals 1/2, and then I'm going to subtract 2 from both sides, so x equals 1/2 minus 2, which is -3/2. So that's my first new x value, -3/2. Okay, my next one is going to be, so I set the argument, -2x plus 2 equal to 0. Divide by -2x plus 2 equals 0, right? Because 0 divided by -2 is 0, and so I get x equals -2. All right, so you can continue this pattern. You get -5/2, and then -3. So those are my new x values. I just took the argument, what's inside the absolute value bars, and set them equal to each of these x values to get the new ones. Okay, so now all I have to do to transform y is, the only thing that's affecting y is the +6. So that's what I'm going to do. I'm going to take those old y values and simply add 6 to them to get my new ones. Sorry, that's not what I wanted to do. All right, so you guys should plot both of these in Desmos, both the parent graph and this guy, and make sure that these ordered pairs are on the parent graph and these ordered pairs are on the transform graph, just to verify yourself there. All right, guys, thanks for watching, and thanks for taking my class this semester. This is going to be the last video that I do instructing, talking about college algebra material. I hope these videos were helpful for you guys, and hopefully I'll see you guys in the future. Thanks for watching.